Hi, this is Ms. Marquedos, and in this class we're going to look at rational functions, which is the other family of functions we look at this unit. So earlier this unit we looked at polynomials, and particularly we started with the power function, a times x to the b. We said that if that exponent b was positive and a whole number, then that y equals ax to the b would be essentially the parent of a corresponding polynomial function. So like y equals x cubed is the parent cubic polynomial. We also noted like that day on power functions that if b is less than 0, so if that power on x is something that is negative but still a whole number, we could say that since the exponent is negative, we could rewrite a times x to the minus b as a over x to the b. That turns out to be what we call the parent rational function. So both polynomial and these new functions we're going to look a little bit at today called rational functions, both of their parents come from the power function. So if we want to look at, a new class of functions, we always look at the absolute most basic version of that class of functions. So the most basic rational function is called the reciprocal function, and is of the form y equals a over x, where a is not equal to 0. So in keeping in line with making things simple, right, if I look at this type of power function, y equals a over x to the b, if we make b equals 1, an exponent being 1 makes things simple in a lot of ways. So that's how we're just getting x in the denominator. And to make it super simple, we're going to make a equal 1 also. So the most basic parent rational function that you could look at is y equals 1 over x, and it's graphed over here to the right. Graph is pretty peculiar. I think it's not something we've seen a lot of or anything that looks like this too often, maybe just like analyzing particular graphs. But this function, this parent rational function, definitely has some notable key characteristics. One thing about this one in particular, and it depends on the equation, but you notice this graph has no x or y intercept. You might think of this as two separate graphs. It's not. They're just sort of two separate parts of the same graph, but no parts cross the x or y axis. You'll notice the graph has a vertical asymptote at the y-axis. That would be the vertical line x equals 0. And also, the graph has a horizontal asymptote at the x-axis, which is the line y equals 0. So that's pretty peculiar. Also, this function's graph has both a horizontal and vertical asymptote. We've seen functions with one or the other, but not both. So that's interesting. And I also think the domain and range are notable here. What's interesting when you look at the graph, and Desmos is going to help us see this a little bit better when we do an actual problem here. The domain and range is pretty simple. The domain is any real number. The only real number you can't put in is x equals 0. So we literally say that x cannot equal 0. And you can see that this graph exists everywhere except when x is 0. We will see that better in a few minutes. And in a similar way, right, the range is actually pretty much any real number with one thing it can't be, y equals 0. And the reason for that is the graph never crosses the x-axis, so y never can become 0. So what is the definition of a rational function? It's actually pretty simple, and it has a particular form. So a rational function, maybe we'll call it r of x, r for rational, is of the form f of x over g of x, where f and g are polynomial functions, pretty important. So most people would say that a rational function is a polynomial function divided by another polynomial function. That means these could be pretty broad, unfortunately, because like the top here, like you could put a cubic, a quartic, a quadratic, a quintic, a septic, something, right? The bottom, you could do the same thing. So there's a lot of option and variations on the types of polynomials that you put in the numerator and denominator, which makes understanding them pretty hard. And so maybe sad or not too sad, but like polynomials, pretty vast family of functions that require some more math to truly understand their behavior, such as calculus. So we won't get into all the nitty gritty, but we will see a good amount of stuff. I would say for us in this course, as a good introduction to these rational functions, we definitely want to be super comfortable with a rational function that looks like this: ax plus b over cx plus d. I would call that linear over linear. We will look at a few others, but what I'm saying is this is the one that I would test you on in the most detail. So let's look at one of that nature in some pretty heavy detail. So number one here, consider the rational function f of x is 4x minus 3 over 2x minus 6. You notice that this function, f, fits the form I was talking about right here. The top is linear, the bottom is linear. Remember, linear functions are polynomials. We don't necessarily tend to think about them that way, but they are. So this function is rational. You can think of it as a fraction function, right, with polynomials, okay? A lot of these questions here, it seems like a lot, but I think a good number of them, we've done this many times, and I think we could motor through these. So part A, find the y-intercept. If I want the y-intercept, I set x equal to 0. So I show that f of 0 equals 4 times 0 minus 3 over 2 times 0 minus 6. So you get minus 3 over minus 6, which is a half. Okay, so you could say your y-intercept is 0 comma half. Maybe some slightly new but usual business happens with part B. How about the x-intercept? If you want the x-intercept, you are setting y or f of x equal to 0. Something sort of interesting, slightly interesting happens here. So I take the equation for f of x. I'm going to leave my self some room here, actually. So I'm taking the equation for f of x, and I'm setting it equal to 0. I think a lot of people kind of look at that situation and say, well, what am I supposed to do with it? One thing you could do algebraically is, I'm not particularly fond of this fraction that I have set equal to 0. And we'll see this happen a lot this unit. What I could do is I could multiply both sides by the denominator. Because, of course, right, if I do the same thing to both sides, then I'm allowed to pretty much do whatever I want. So on the left-hand side, they simplify away. On the right-hand side, because it's 0, anything times 0 is just 0. So you end up with this, simply 4x minus 3 equals 0. And so that is a little bit interesting and a good thing to think about for your future. This function, f of x, which is a rational function, is equal to 0 when the numerator is 0. That's pretty important. If I forget that, I'll see it come out in the algebra, but that's pretty interesting. More on that to come. So I solve this little equation here, and I get x is 4/3. So I could say the x-intercept is 4/3 comma 0. Okay, let's shrink that a bit and keep moving. We got lots of things to answer here. C, for what values of x is f of x undefined? That's something we've talked about a little bit all year long. Undefined is the value of x which causes the function to either basically divide by 0 or square root a negative. With this type of function, we won't be square rooting any negatives, so I'm assuming I don't want to divide by 0. So let's maybe make a little note here for part C. So if you want to figure out where f of x is undefined, what you need to do is take the denominator, right, which was 2x minus 6, and set it equal to 0, because you would like to find the value of x that if you plug it in, you will end up dividing by 0, which we know we are not allowed to do because it's impossible. It does not yield an answer. So I add the 6, and I divide by 2, and I get x is 3. So we would say that f of x is undefined when x is 3, or sometimes people will say that f of 3, in other words, when you try to plug 3 into f, you will not get an answer. So it is undefined. at 3, f of 3. Okay, pretty quick. I mean, we're already up to part D. So based on your answer to part C, state the domain of f. You see, when we looked at that rational function, the parent rational function, there was a particular value of x. It was only one, too, which was interesting. It was just one value that could not be in the domain. The reason it's x equals 0 is if you try to plug in x equals 0 into this simple function, you end up with the denominator becoming 0, which is no good because then you are attempting to divide by 0, which you can't do. So that is what this number 3 does to this function. It makes it undefined. So part D, if I wanted to state the domain here, I might write like domain of f. And one thing you notice, like depending like what the domain is, you find that people write the domain in different ways. For this type of domain, I think a lot of times you see people use set notation. So they'll say something like this: the set of all x that belongs to the real numbers such that, and then they'll write x cannot be equal to this number 3. Okay, next thing, which is also connected, somewhat interesting, part E, based on your answers to part C or D, or maybe both of them, what is the equation of the vertical asymptote to the graph of f? Again, back to this basic one, it's kind of interesting, right? That value of x that's not in the domain, that one value, is the value of x that makes the denominator 0, right? Which makes you divide by 0. So that makes you undefined. If you look on the graph, what you end up seeing there is at x equals 0, which happens to be the y-axis, you have a vertical asymptote. So for this function, the equation of the vertical asymptote, so I'm actually going to write this because we should be clear. It's interesting how the question in C, D, and E are all sort of related to each other. They're all sort of referring to the same thing. So the equation of the, and we could abbreviate here, vertical asymptote, V dot A, is x is 3. Cool. And now for f, we're going to sketch it pretty quickly, I think, but note some of the characteristics and actually now ask the question about the horizontal asymptote. So I'm graphing this one from number 1. It looks a lot like that parent rational function, 1 over x, but there's some differences. It's been moved. Like, for instance, because of things getting moved, this graph actually does cross the x and y axis, which 1 over x does not. Now, I said that at x equals, did I say 3 or did I type something in wrong? I think I typed something in wrong. Hopefully, it is minus 6. Whew, thought I messed it up real bad. Okay, that changes things. Again, notice this one still has an x and y intercept. So let's see. We're saying that there's a vertical asymptote at x equals 3, so let's draw that in. And you can see that is this vertical line that both ends of the graph will come infinitely close to, but never touch. Both sides. It's pretty nifty. You also notice there's sort of a horizontal line there that it seems that either ends of the graph do not touch either. It could be hard to see, but with Desmos, right, I can play around and get the zoom right. To me, it looks like the horizontal asymptote is at y equals 2. And I could check, right? Does the graph like get infinitely close to that line horizontally and never touch it? Yeah. So actually, just from using Desmos to help me a little bit, I was able to find the vertical and horizontal asymptotes. It seems though for the vertical asymptote, it was pretty easy to find algebraically. There is a trick to find the horizontal asymptote, but let's sketch that real quick. And we also see where my axes intercepts are, but we found that in part A and B. So one thing I do when I'm graphing these rational functions, or rather sketching them, is I always draw my asymptotes in first, right? So there's one at x equals 3, so I'm drawing that in dashed. Remember, these are not actually part of the graph, so you don't want to draw them in as solid lines. So there's a vertical asymptote at x equals 3. There is also a horizontal asymptote at y equals 2. And it is good form to like label your equation. And so now, I have the well, what else can I do? I can mark, ooh, I noticed I wrote the wrong answer here. It's good to make mistakes. I wrote 4/3. It's 3/4. 3 divided by 4 is 3/4. Cool. So I can mark those off, which is also a good idea. What I like to do is I like to mark almost all of my key features, and then pretty much I'm just connecting the dots and stuff. This would be 3/4. So I got my asymptotes, my x and y intercepts. So let's see. So my graph looks something like this, right? You want to make sure that the line does not cross these asymptotes, or rather the graph does not cross these asymptotes. Here's the other piece of it. That's my sketch. I am using Desmos to help me a little bit, but realize almost everything there, maybe with the exception of the horizontal asymptote, I was able to find algebraically by analyzing its equation in parts A through E. F is my sketch. Pretty cool. What do you think the equation of the horizontal asymptote is? So we saw that before. That's the next part. I think it's y equals 2. That's just based on what I played around with in Desmos to see happen. So I think it's y equals 2, horizontal line. The interesting question is, how can you see the location of the horizontal asymptote? Because that's what this is all about, right? Like ultimately, what is interesting is that almost all of these graphical characteristics, not even almost, all of them, can be seen by analyzing the function's equation, right? That's the beauty of algebra. So how would I be able to see what the horizontal asymptote is just by looking at the equation? It's not super obvious. What I'll say is this, and then I will explain it to you with end behavior. If you want to know can we write this above here? Sorry, I didn't want to go too on a tangent here, but it's worth it. Actually, how you figure out where the horizontal asymptote is for a simple rational function like this is it's the ratio of the highest power of x, okay? So what I'm saying is how you could end up with y equals 2 is by saying it's really just 4/2, which comes out to 2. Now that's just, right, that's like some sorcery, right? Like, oh, that's trickery. Why does that happen? It's actually because of end behavior, which is interesting, which is the last part here, and then we'll just move on finally. So this is a long question. All that to say is, I think like this level of rational function, we should be able to answer any and all of these questions pretty smoothly on a quiz like this week. Describe the end behavior. So check this out. We played with end behavior a bit last week. Remember, when you want to talk about left end behavior, what you say is as x goes to negative infinity, left end behavior, so you're going far to the left, where does the graph of f point to? Like, where is it going? Like, where does this arrow or tail point to? That piece of the graph, this left tail, it wants to get ever and ever closer to the number 2. It'll never get there, but it'll get infinitely close. This is actually the notion of a limit in calculus in some sense, at least part of it, and from one perspective. So, like, doesn't the graph want to get super close? Doesn't the y values want to get super close to the number 2? 2, 2, 2. If you talk about the right end behavior, okay, then you're saying what happens as x goes to positive infinity. So what happens to the graph as you go super far to the right? Again, look at that. What's the right tail sort of pointing or heading towards? Desmos shows you this much better, but it's also heading towards 2. So that's interesting. Both ends of the graph, right, they both head towards 2. One from above 2 and one from below 2, which is also interesting. So both ends go to 2. This is really what it means to have a horizontal asymptote. But again, you're verging onto calculus. Cool. So I want to make sure I'm good with that. I will see one like this in my homework for sure to make sure I'm peachy keen. But let's just look at a few other things. So if somebody gives me a rational function and things are, workable, I should be able to tell what the domain of a rational function is without graphing it. If I would like to determine the domain of any function that is like fraction in its nature, right? What I want to check is, are there values of x that make the denominator 0? So my question is it possible that f of x is undefined, is what we say. Which means, right, that would happen if there's a value of x that you plug into the denominator that comes out to 0. That's how we check. That's a quadratic equation, but, magically I can factor this. X minus 8, x plus 2 equals 0. So I got two possibilities here. X is positive 8 or x is negative 2. These two numbers, right, will make the denominator 0, which is another way of saying f of x is undefined. When you find those values of x, what we're saying is when you go to write the domain, we're saying that those two numbers, 8 and negative 2, cannot be in the domain. Because if you try to plug these in, what they're going to do is make you divide by 0, which is an impossible task. Nobody can do it. There's no secret to it. It's not defined to do that. You cannot divide by 0. So if I was going to write the domain of this function, any value of x I want to plug in is cool. Any real number. However, there are two, so I put my bar such that cannot go in there. It can't be 8 or it can't be negative 2. Cool. That's all we're saying about being defined, dividing by 0, right, and having your domain. And so you see they wrote it a little differently here, or I did at least, but I think you get the picture there for the domain. Also, what would be interesting to do is check what is here. So can we do, we'll skip around here a bit, but I think to do, come on, it's like blurry. Oh boy. During the video. I think we're actually okay. Or I just back out and in. Of course this would happen mid-recording. Let's see if I can get back. Rational functions. Wow. Let's see. Ooh, come on. Whew. Scary. Sorry, you can just skip that anyway. It's not on Edpuzzle. So let's look at a rational function where, like I said, these things could look very different. They could have a lot of different behaviors, and it really depends on what type of polynomials you can have on the top and the bottom. This one has a linear on a top, but the bottom is quadratic, so that's pretty different. You have Desmos to help you, or any calculator, graphing calculator, but there should be some things that I can analyze and determine about this function by analyzing its equation. So same kind of thing for part A here, like what values of x is h of x undefined? If you'd like to know when this function h of x is undefined, what you have to figure out is what are the values of x that make your denominator 0. Which means literally take your denominator, set it equals 0. We're not wonderful at factoring these. I think some of us dislike it, but I don't want to waste our time like beating this to death. But how I do it is I would end up rewriting this as 2x squared plus 12x minus x minus 6 equals 0. I will group my terms, right, pair them off. So I take out a 2x from the first two. I take out a minus 1 from the second two. And those binomials match, and so I am able to factor. I'm very excited. I set each of those equal to 0, and I have two different possible values of x. It would be negative 6 or a half. Okay, so I mean, solving quadratic equations, that comes up a lot, it seems. Cool. So from part A, what I'm ranting about here is part B should be pretty straightforward because it's very well connected. What would the domain of h of x be? Essentially, it's any value of x except these two. Those two make the denominator 0. So if I was going to write the domain for this type of function, and you could write it different ways, but because it's only two values that you're excluding, a lot of people tend to write it this way. So they say, look, it could be any real number x such that, or as long as x is not negative 6 and, or I think if you put and or there, it's nobody's going to care. X cannot be a half. So by finding the values of x that make the function undefined, you also find the domain. You find the values of x that should not be in the function's domain. Cool. And then again, part C here, also connected very closely to those two, is state the equations of the vertical asymptotes to the graph of h of x. So this is kind of a lie, and you learn this in pre-calc and calculus, both of them, that, so what I'm going to tell you is sort of a lie, that the values of x where the denominator becomes 0 are where your vertical asymptotes are. That is not always true. It will be true for this one. It will be true for any one I give you, but that's not completely true. But there's two of them in this case, and we'll see it when we graph it. So your equations of vertical asymptotes, the first one we looked at, right, only had one vertical asymptote. This one has two, which is possible. You could have many vertical asymptotes, as we'll see later in the year. Cool. So A, B, and C are all half this question are very closely connected. D, find the x and y intercepts. I should be able to find those things, I think, without too much trouble for any function, hopefully. We always get the y-intercept first because it's super easy because I'm plugging 0 in. So f of 0, or wouldn't be f, would it? It would be h, because that's the function's name. H of 0 is 0 plus 5. I mean, right, you're plugging in 0 for x's, right? So wouldn't it be like, I mean, I guess you could write it, but you're plugging in a bunch of zeros, so should be easy to see. It should be, what are you left with? 5 over negative 6, so you have minus 5/6. So my y-intercept is 0 and negative 5/6. And then, let's see, new color. We need the y-intercept, or sorry, the x-intercept. So I would set h of x equal to 0. Here's sort of where that pro tip comes in. I'll let you think about this on your own time a little bit, but you saw when we did part B of number 1, I told you that it turns out that when you set a rational function equal to 0, or really what you're asking is when you have a fraction and you have it equal to 0, what is it that has to be true? It has to be the numerator that's equal to 0. It can't be the denominator, because if it was the denominator, then it becomes undefined, which is something different. So if I'd like to know when this thing equals 0, which actually looks quite complicated, right? Like if you take this and set it equal to 0, you might be like, oh my God, how do I find that? Turns out it's pretty simple. This will be 0 when the numerator is 0, which is actually like, oh, okay, negative 5. So you have an x-intercept at negative 5, comma 0. So I found my x and y intercepts as usual without too much trouble. E, sketch the graph showing its key characteristics. Obviously, look, I encourage you, if I ask you to do anything like this, use a graphing calculator to help you at this time. To do that stuff without a graphing calculator requires some more math that we're not going to do. So let's check. That is this function. We can get rid of these, and let's zoom. So as I said, this is a weird looking thing, right? It's very different looking. This function has two vertical asymptotes, actually. We found them algebraically. It's at negative 6, and then the other one was at positive 1/2. Where's x? 1 divided by 2. Maybe change the color for some contrast. good enough, right? So this one actually had two vertical asymptotes, and it happens to be at the two values of x that make the denominator 0. Pretty cool. Okay, so other than that, it's pretty complicated to figure out exactly all of these things. I did find the x and y intercepts already, right? Those are them. That matches what I found algebraically. There is one other thing we noticed, that the graph does sort of have a horizontal asymptote at the end. We'll talk about that a little bit, but so how would I actually graph this, right? Like, how do I draw a decent sketch? Like I said, I try to draw the asymptotes in as best I can beforehand, and then sort of worry about the intercepts and put it together. So I have one at -6. So, sorry. Let's do this. -6. So I'm just drawing a dashed vertical line, right? Like, it doesn't have to be perfect. It has to be decent enough. And then you have another one at a half, which is like pretty close to the y-axis, right? So again, doesn't have to be perfect. But if you label it, that's kind of what makes it okay. Where were your intercepts? So, so the x-intercept was at like -5. So that might be like right here, roughly. And then the y-intercept was at -5, 6. So that's like a little bit less than -1. So maybe something like that. And all I'm going to do there really is, I'm going to connect those points, and I'm going to do my best to kind of match the shape that I'm seeing here. But again, I do notice, like, you see the graph does cross the x-axis here. But then, like, this end of the graph, you see it, like, creeping towards the x-axis, and then it, like, never touches it. There's actually asymptotes there, which is a pretty complicated thing to ask somebody in Algebra 2. So that's why we kind of don't beat you over the head with that. So anyway, if I was going to piece this together, it would look something like this. I have, right, put your tails on the graph. Connect those key points, put your tails, and then, make sure it looks like how it should. It's not perfect, but there's a lot of key things, exhibited in that picture that somebody might want to know about that function. Cool. And this is what I'm talking about with f. I probably will not ask you to figure something like this out. It's just a little too much for us right now, but does h of x have any horizontal asymptotes? It does, right? It's actually the x-axis. I see it here. Like this, so these two ends of the graph, like they want to approach the x-axis, but they'll never touch it. It's a little bit weird because this portion of the graph actually crosses through it, and we're told that graphs are never allowed to cross their asymptotes. That's also kind of a semi-lie. I would just say for f that the equation is y equals 0. Cool beans. So, right, I should be pretty okay focusing in on just basic key characteristics, behavior, sketching the graph of a pretty simple rational function with a focus on rational functions that are linear over linear. Of course, right, with functions come their algebra, and it would be nice if I could utilize a lot of the algebraic things I've learned about functions earlier in the year here. So just in the interest of not boring you too much, we'll do maybe A and B here, and then in number 5 we'll do maybe just B. So I give you that g of x is 3x minus 2, and f of x is 2x plus 1 over x plus 5. Part A, find f of g of 2. This, my friends, is your favorite thing. I'm trying to make it your favorite thing, but it's been a fight. It's composition, right? You have to work your way from the inside out. So the first thing I need to do is calculate what g of minus 2 is. So I'm leaving f alone. I'm not doing f right now. I'm doing g. G is 3x minus 2. So g of minus 2 is 3 times -2 minus 2. And right, so What's in orange is the same thing. You see f is in both places, right? On the left and right. That's because I haven't done the function f yet. I've done g. So I simplify what's inside there. So 3 times negative 2 is negative 6, minus 2 is negative 8, correct? Hopefully, yes. So now I have to find f of negative 8. That's just plugging negative 8 into f of x now. Once you get towards the end, it becomes like basic function notation. So I'm replacing all of the x's in f of x with what? Sorry, negative 8. I lost my mind for a second there. Anyway, so the top is negative 16 plus 1. So what would that be? Negative 15 over negative 3. So final answer would be positive 5, right? So kind of like a therefore thing here. I would say that f of g of minus 2 comes out to 5. Maybe look at B. It's been a while. I think we haven't talked about composition a lot. You can't forget about composition. It's a very important idea. So that is, part B is different in a couple of ways. The first way, right, is the way I'm writing the notation. That is f composed with g of x. It's not fog. This is not multiplication. What it really means is that you would like to take g of x and place it inside of f of x. You're literally substituting the function g into f. So what I like to do from here, and notice there's no number in here, it's just g of x. So what is g of x? It's 3x minus 2. So I'm still not touching f. F is still there. What is g of x? It's 3x minus 2. So you see I've made a substitution, and I'm starting on the inside. G of x with 3x minus 2. So I am literally now going to replace every x I see in f of x by 3x minus 2. Do that, carefully. I think easy to make a mistake here. So 2 times 3x minus 2 plus 1, right? And then the bottom is x, so it's 3x minus 2 and plus 5. And all I have to do really is simplify at that point. It's just clean it up. So distribute the 2, 6x minus 4 plus 1. On the bottom, I'm just combining like terms, so that's 3x minus or plus 3. I don't know why I lost what I was thinking about there for a second. 3x plus 3, right? Yeah, I think I'm okay. And then I guess combine on top, so you have 6x minus 3 over 3x plus 3. And I think that's pretty good. That's simplified. One thing we will find this week and next week is a lot of times that expression can be simplified even further. So, this really changed from something about composition to a bunch of simplifying, which is hard sometimes. I think from these two expressions, right, I could factor a 3 out from both of them. And what that allows me to do is simplify a little bit, right? The 3's can be simplified away. I'm going down pretty far. So this simple composition actually turned out to be quite a bit of work, right? But all in good health. It's like your math veggies. Maybe that's why I chose green for vegetables. And something else, that we learned earlier this year about functions, and we'll do really quick right here. I think we'll do part B because it's a little bit harder maybe. I learned how to algebraically find the inverse of a function. So I should be able to do that in theory with rational functions. So let's do part B. Good review too, I think, of just big ideas. So what I usually like to do, and I think you can do some of this mentally than writing, but first thing I do is if it's g of x, I change it to y because it's easier to move around. Okay, now, the first thing you really do when you're trying to find the inverse of a function algebraically is you swap the positions or the roles of x and y. So anywhere I see a y, I'm going to write x. And anywhere I saw an x, which is actually in two places, right, top and bottom on the right, I need to replace those with y. And now my job is to solve for y. But this actually seems pretty tricky because just algebraically you have a y in the numerator and denominator. What I'm going to do, and this will become more commonplace throughout the rest of the unit, but I'm actually going to multiply both sides by y minus 3. The reason I'm doing that is because nobody really wants to deal with a fraction. So just by doing something to both sides and rewriting it, at least I get rid of the whole fraction thing. On the left here, right, you have x times y minus 3. You need to distribute it, right? It's x times both of these things. So my next line down would look like this. xy minus 3x equals 2y plus 5. Okay, remember, your job here after swapping the positions of x and y is to solve for y. I'm not really close to solving for y here yet. I have y's on both sides of the equation. So what I'm going to do here is I'm going to add 3 to both sides. 3x, excuse me. Let's do this slowly, right? So I'm adding the 3x over. What's interesting is there's nothing to combine it with, so I'm just kind of sticking it off to the side. I'm going to subtract the 2y over to the left. So you have xy minus 2y equals, I'm going to write this as 3x plus 5. I think that's cool, right? You know, you really can't combine these per se because they're in some way not like. But what I can think about doing here is factoring out a y as the greatest common factor. So I'm going to do y outside x minus 2 equals 3x plus 5. And then I'm going to divide both sides by x minus 2. And lo and behold, you've actually algebraically solved for y. That's much trickier than some other ones we've had to deal with this year. So what I'm saying is at this point when you have solved for y, what you have found is what we call g inverse of x, the inverse of g of x. Okay, so just a little peek into the world of rational functions. If you want to delve into them much, much deeper, well, you're going to have to take more math, which I assume. Anyway, please let me know if you have any questions. Hope you're doing well. Talk to you soon. Take care.